Great. Are we all ready to start? Okay, so welcome back from lunch, everyone. I hope you all enjoyed your lunch. We're going to begin our next talk, which is by Dr. Locke. He's a resident professor here at FAU. He studies graph theory and combinatorics and game theory. And today he's going to be giving a talk on looks like subtraction games, which is on combinatorial game theory. So please put your hands together for Dr. Locke.
Let me just check. The people who are at another site, you can hear us?
Maybe they're muted.
I unmuted here. Can you hear now?
Okay, just to.
Yeah. I'm going to assume they can hear, and if you see a chat show up saying, hey, we can't hear you. Okay, so I'm going to talk about combinatorial games, also called games of no chance, because there's no dice, there's no cards, there's no coin flipping, things like that. All right, so there's no probability involved in these games. Okay. Now, I am going to make you do a little bit of work. This is not all going to be just me talking. Okay. There we go. So just quickly, I've got a list of things I'm going to try to get through. If I get through them, that's great. If I don't, well, too bad, right? So I'm going to start with a very simple game, and I'm going to talk about what happens if I'm playing two games at once. There's something called Grundy numbers, which are really 3 and 4 here. Grundy numbers and NIM are, in some sense, the basis of combinatorial game theory. Games fall into two types, in my mind. Ones which I can solve, and ones I can't. No, ones I can solve, which generally are where these techniques work, and then ones where those techniques just don't work at all. And then you have to try to do other things to figure out what's going on, okay? So I'm going to do a fairly low-level talk here, but when I get to this section on other games, I've got like 5 or 6 unsolved problems in there. So you just have to have the patience to stick around if you think all this stuff is too easy. So the very first game is you've got a pile of checkers. And you can spread these around and play if you like. But the idea is let's just put a few of them on here. Okay. And so our little pile, oh, that's got 6 checkers in it. Do you want to go first or second? Okay, so the rules are going to be on the table, there's a heap of checkers. There's 2 players. They're going to alternate turns back and forth. Each player takes either 1 checker or 3 checkers or 4 checkers. And if you have no possible move, you lose. The other player wins. So do you want to go first or second?
Go first.
You're going to go first with 6. Go ahead.
All right, so I can take 1, 3, or 4.
1, 3, or
All
4.
right, I'll take 4.
Good move. All right, he's played before. Because now there's only 2 left. I have to take 1.
And so I'll take
And
the
he
last.
takes the last one, right? So what you should do, I want you to think about in general, do you want to go first or second? All right. Maybe I should phrase it as, when do you want to go first and when do you want to go second? Okay. So if anybody wants to play a little bit, have some. You guys don't like toys in your class? Okay. So Mr. Gold here has answered the first part of what I'm going to do very simply, is if we play a couple of small games, right, to get an idea what's going on, I always try to generate some data. I can't just look at a game and say, oh, we do this to win, right? You have to look at the game, you play a few small games, you try to see if there's a pattern, and if you see a pattern, then you try to prove to yourself that that pattern is really there, right? So here's the first couple of questions you should ask yourself. If there's 0 checkers in the heap, who should win? That one's pretty trivial. If there's 1 in the heap, who should win? You should do the same thing for 2. I said, if there are 3 in the heap, who should win? Right? So obviously, if there's 0 checkers in the heap, who wins, the first player or the second? Well, the first player can't move, so the first player loses, the other player wins. So 0 is a loss for the first player. If there's 1 checker, the first player takes that 1 checker. So the second player doesn't have a move, the first player wins. Looking like you want to ask a question.
It's not a question, but because I'm not familiar with this, so yeah.
Okay. Well, one thing is if we
Try
do,
to analyze.
yeah, if we do another example, so I said 1, 0, 1, or 3. I left 2 out, but if there's 3 checkers, well, the first player can take all 3 checkers, so they win. Because the other player can't move. 3 is really easy, right? So the first player wins. Actually, the first player could have also taken just 1 checker, which leaves 2 checkers. The second player now has to take 1 checker, and the first player again wins. So what happens here is the first player had more than 1 way to win. That's okay. If you can win more than 1 way, all you really care about is, can I win? Right? Okay. Okay, so I'm going to give you some notation. And it took me a while to get used to this notation myself, but so we've got a position X. See if I can move that.
I think you can, yeah, you can move the talking thing.
Okay. So from a position X, if the first player can force a win, we're going to call that an end position. If the person who's about to play can force a win, we're going to call it an end position. That's actually a very standard term. So it kind of means the next player can win, right? And if the second player can force a win from that position, we call it a P position. So the previous player can win. So the P is for previous, the N is for next. I showed these slides to my wife. She says, why do you have the N and the P in different fonts here? Well, so you can tie them with the word N position and P position. All of the moves from a P position have to end up in an N position. If you're in a bad place, it's because you got no good moves, right? All the moves that you would make, let the other player win. And if you're in an N position, then at least 1 move results in a P position. Maybe some give you a bad position. Some give you a position where the next player wins, but at least 1 gives you a position where the next player is going to lose if you play properly. You get used to what N position and P position mean? Now, move outside the range. There we go. So here's that same game. It's still the 1/3/4 subtraction game. So you can look at 0, the first person loses, so it's a P position. 1, the first player wins, so it's an N position. 2, the first player loses, so it's a P position. And you can go through and you can calculate for the first few values, right? So I worked it out up to 7 here. How many of you see the pattern already? Nobody volunteers? Oh, you see the pattern? What's the pattern?
You can make a move to put it in 0, 2, or 7, or congruent to 0, 2, or 7 mod 7, or sorry, 0, 2 mod 7.
Yeah,
right?
the 0 mod 7 and the 2 mod 7, and this is the 0 mod 7.
Yeah.
So if you've never seen modulus before, it just means the remainder when you divide by 7 is 0 or 2, right? Okay, you don't need my next slide then, because my next slide is if you couldn't see the positions, you couldn't see the patterns, you run some more data, and it's really not that hard to run out some more data. And now you start seeing which ones are P positions, which ones are N positions. So 0, 7, 14, 21, and so forth, those are all P positions. 2, 9, 16, and so forth, those are all positions. Right, and all the rest are end positions. And here's actually the things that work for each of those positions. So now you know how to win this game. Right? Anybody who doesn't know how to win yet? Want to make it so that what's left in the pile is 2 more than a multiple of 7 or is a multiple of 7. Okay. Well, just nice and simple. Yes.
Does that, can you go back to the previous slide? I'm sorry.
Yes. It's a magic of technology. You erase the blackboard and then it comes back.
Does this mean that all games of this specific game is determined, that as in there's always like an optimal move to make for,
So in this one,
regardless of what, in a way, no matter what?
wherever I start,
Yeah.
I can decide, I can tell whether it's an N position or a P position. If it's a P position, I'm in trouble.
Yes.
Okay. If it's an N position, I've got a winning move. I'm going to take that winning move. If it's a P position, I'm going to hope my partner doesn't know anything about how to play. And I'm going to make a small move and hope that they mess up. Okay. So, I have, there's 21 checkers there. All right. Oh, I'm in a bad position. I take 1, leaving 20. Well, if they don't know they're supposed to take 4, whatever they do, if it's not take 4, I can now win. Right. So I can make a small move and hope they don't really know how to play or that they miscalculate. That's also a possibility, I mean, even the best of us add 2 numbers and get it wrong sometimes. Okay. So I thought your question was going to be this one. So how about if I said instead of taking 1, 3, 4, you can take 1 or 4 or 5. Okay, I'm not going to tell you how to play that one. Just that's where if you're bored with the rest of my talk, you can just think about it. But I'm going to think about something different. I'm going to say, suppose we actually want to play, instead of with 1 heap, we play it with 2 heaps. Okay. Oh, you want to play with 2 heaps the same size? Well, that's kind of boring. Well, so he's put a heap of size 6 and a heap of size 7 here. Makes it easy because I'm just going to take 1 from the 7.
I thought I was first.
So you wanted to go first, all right.
I thought I was first.
So what you tried to put down was the case where the 2 piles were the same. Okay. If the 2 piles are the same, how are you going to play? Who should go first? Yeah.
I guess I'm a little confused about the rules of the 2 heap game.
You take from 1 heap or from the other.
How many?
Either 1 or 3 or 4 in this game.
Oh, okay.
Okay. I'm keeping it for a little while to 1,
So
3,
you're
4.
not like changing 1 heap to another heap, you're actually
Just
removing.
removing some from 1 heap.
It looked on the table as if you knew.
I just pulled it over to a junk pile. Okay. So he had made a pile of 6 and a pile of 7. And I just said, well, gee, I should make that a 6. Okay. And then if he can decide on either one of these piles. So which pile do you want to move from?
Doesn't matter. I'll take the first one.
From first pile, how much?
Well, my winning move last time was 4, so I think I'll just do 4.
Okay, so he's going to take 4, so I take 4. Okay. Good strategy building up here.
I think
Whatever he takes from one pile, I take from the other. Okay. So if the 2 heaps have the same size, and I'm playing the same game on both heaps, all right, and I get to make a move in 1 heap or in the other heap, I don't get to make a move in both heaps at once. I can move in heap 1 or in heap 2. All right. And if the 2 heaps are the same size, I let him go first because I'm generous. Every time he makes a move, I make exactly the same move in the other heap. Okay. All right. So if you're surprised that that's called a mirror strategy, tell me about it. Anybody surprised? Okay. No, nobody's surprised. Okay. It's like you're playing in a mirror, right? Something happens on this side, same thing happens on the other side. So that's easy, right? If the 2 heaps have the same size. Well, I guess the next thing must be, what if the 2 heaps have different sizes? Okay. you have an idea of the strategy. Somebody give me size of two heaps. I'm still gonna play 1, 3, or 4 away. So
6 and 11.
6 and 11. Okay. You want to go first or second?
I'll go, oh, somebody said second. I feel like they know what they're talking about, so I'll take a lifeline and I'll go second.
Okay,
Let's see.
good, good. Because now I have to think, you know what I mean? So. I think you've given me a nasty one because,
Glad I could be of help.
good, good, good. I can't take 2 from there.
So, I guess I'm not sure what the end is. Who, like now there are two heaps. So if one of
The
the
one who
heaps
takes
is,
the last one totally, right?
oh,
When you've
okay.
exhausted both heaps, the one who takes the last one wins.
Oh.
Okay? All right.
So-
Last one.
So what, like,
So I don't know what to do here, so I'm just gonna play and take 1 from the 10 and 1 from the 11, making 10. How's that? Okay? And now you get to play. I could have worked out how to play, but
Yeah.
you want to take 4 from which one?
No, I said the same, one.
Oh, you want to take 1?
Yeah.
He's asking for 4, you're
yeah,
asking
I
for
want,
1.
I want to do 4.
Okay, you want to take
do 4 too.
4.
4 from which one?
10.
Oh, you want to do 4 from here?
No, second from the other heap.
You want to do 4 from this one? Oh,
Let's
good.
try that.
Okay.
Oh, no.
Maybe you give me a chance, I don't know.
There's a move here.
Well, why don't I make this one, take 3 off of that one, I leave a 7 and a 2.
Let's take 1 from the 7.
Okay, so you make this a 6? Well, I'm gonna take 4 from there and I leave a 2.
Oh.
So at the beginning, I didn't know how to win. We got down to a point where the game is simple enough that I can sort of see what to do after we get to a certain point. Actually, when this was 10 and this was 6, if you'd taken 4 from this pile, it's dead. Okay? I know, I figured that's what Dr. Hoffman was saying. Somebody else said, the other pile, I said, okay, I'll run with it. So one thing you might say is that, if the 2 piles differ by a multiple of 7, maybe then you're not in bad shape, right? So, if I have here 16 and 23, these differ by a multiple of 7. If you were to take 4 from this one, maybe I should take 4 from this one. Right? And now they still differ by a multiple of 7, and I keep trying to play that way. Right? But that's all well and good until I get down to something like here's a 2 and here's a 9, and the person takes 3 from this one. I can't take 3 from this one. So I can't quite do that, right? So I can try to take the same number, whatever they took from one heap, I can try to take the same from the other heap if there's enough, and I might be in okay shape if the 2 piles, 2 heaps are differing by a multiple of 7. But what happens if they don't? Okay, so here's that 9 and 2 example, right? The player takes 3 from a heap of 9, the second player can't take 3 from the heap of 2. So I can't do that strategy of trying to keep the difference in multiple of 7. Okay. So maybe it's time to add some mathematics into this. Not very much mathematics, a little tiny bit of mathematics. What I'm going to do is I'm going to define a number called the Grundy number. Actually, I heard somebody at the conference pronounce it as Grundy. So I don't know, maybe that's the pronunciation, who knows? I've always called it Grundy number. Yeah, it's German, so Grundy might be right.
You might be right.
Okay.
Right, is true.
So what I'm going to do is I'm going to define these numbers called Grundy numbers. And so to begin with, I'm going to say, if you give me a set of integers, I should have said here that doesn't contain all of the non-negative integers. I don't really care if it's got negative integers in it, but I don't want to use all the non-negative integers because then the next line is not going to make sense. This max, which is minimal excluded, right? The minimal excluded element of S is the smallest non-negative integer that's not in S. So if S already contains all the non-negative integers, then I have the minimum of an empty set, and that's kind of weird. So as long as the set's not empty, then I can take the minimum element of that set. Okay? So the minimal excluded, which I just say max of S, is the minimum K, which is an integer, K is not in S, and K is greater than or equal to 0. Does that definition make sense to you? It has to be a test somewhere. So what's max of 50381? Gave this quiz to my wife and she got it.
Are we not supposed to take a set which is not all non-negative?
So the set has to be the set of integers, but I don't want to take all of the
Yes.
non-negative integers. So this doesn't have all of the non-negative integers. It has some of them. Okay? And I want the max. I want the minimal excluded element. So 2, right? Okay. And 3 or 4 people think, well, the answer is 2. Okay, so you have an idea what this max means now. You look at the integers that I put in here, and starting at 0, you can say to yourself, is 0 in there? If 0's not in there, then the answer is 0. If 0's in there, but 1's not, then the answer is 1. If 0 and 1 are in there, but 2's not, the answer is 2, right? So it's just the minimal excluded. Okay. So the Grundy number is going to be, if you have a position X, let's look at all the places I can move to, right? So from one position, I can make lots and lots of different moves. All right. Well, each one of those is smaller than the thing I'm looking at, right? So each one of these is somehow smaller than the position X. So I'm doing things like taking coins away. The heaps are getting smaller, right? Whether I'm looking at one heap or a pile of heaps, the total number of coins in my heaps is going down. And so what's happening when everything's getting smaller is this is basically an induction. And I never write the induction that way. I don't say, well, let's look at the base case. Okay. So I look at all the games that you get to from X with one move. I calculate the Grundy numbers of each of those games. And to get the Grundy number for the position X, I take the minimal excluded element of this set of Grundy numbers of all the subgames, right? That's a mouthful. Not very hard, but it takes you a couple of seconds to wrap your brain around that one. Okay. One of the nice things about this is that from that definition, if the Grundy number of X is some number K, then for any integer J, which is less than K and bigger than or equal to 0, there's some position Q sub J so that, that we can reach it from X in one move, but the Grundy number of Q sub J is J. Right? Because when I make this list of all the values, I make this list of all the values that we can reach. If nothing reaches J, then the Grundy number of X wouldn't be K because K is bigger than J. If J is not in the set, why did I pick K? Right? I picked the smallest one that's not in the set. So all the numbers, if the number is K, all the numbers 0, 1, 2, 3, 4, 5, 6, 7, up to K minus 1 are represented in this set. And this is really important. This is really important in how Grundy numbers work. I'll let you wrap your head around that for a minute. It won't be a real minute. Okay, so let's go back to this 1, 3, 4 game for a little while. And we're going to look for a few small n's. We're going to write down what the Grundy numbers are. So for n equals 0, there's no move. So the Grundy number for 0 is the max of this
You
empty
didn't
set.
define it that way.
What's that?
You didn't define max the empty set to be zero. You didn't define it at all. did you?
I said, actually, the mix of the empty set is actually not too bad. Mix of all the integers would be a problem. So what happens here is we're looking at what's the smallest non-negative integer that doesn't show up in this?
Zero.
See, 0 doesn't show up in here. So the answer is 0. But if you give me one where all of the non-negative integers showed up inside the brackets, then I wouldn't be able to define what happens here. So then I would have that I'm taking the minimum of, see, this excluded part would be the empty set, would be the minimum of the empty set. All right. So here, this is the minimum of what's excluded by this. So that's all the non-negative integers that would be excluded. And then I take the minimum and that's going to be a 0. Okay. So if I do n equals 1, there's only one possible move. That's to take the only checker. The empty heap has Grundy number 0. So the Grundy number for 1, I'm just going to write the number of checkers. I'm just going to write that as the definition of what the game is. And you're saying the game is represented by the number 1 or by the number 2. Okay. So I'm just looking at one heap here. So the Grundy number 1 is the max of, well, the only thing I get to is a position which has Grundy number 0. So I'm going to get a 1. Okay. And the Grundy number for 2, well, there's only one possible move. That's to take 1, it leaves a heap with 1 checker. We just saw that has Grundy number 1. So I'm going to have the max of the set with a 1 in it. And 0 is not in that set, so the Grundy number is 0. This is easy enough, but it's just a lot of little calculations. How about for 3? For 3, I can move from 3, I can move to 2, or I can move to 0. Both of those positions have Grundy number 0. So I just wrote both of them down here rather than just one, right? So I can take all 3 away, or I can take 1 away, and I get 0 for the Grundy number in both cases. The minimum excluded is the 1, so Grundy number for that is 3. Okay, so just to continue on a little bit, if I go for 0 is 0, 1 is 1, 2 gives me 0, 3 gives me 1, 4 gives me 2, 5 gives me 3, 6 gives me 2, 7 gives me 0 again. And actually, it starts repeating. So it goes 0, 1, 0, 1, 2, 3, 2, 0, 1, 0, 1, 2, 3, 2, 0, 1, 0, 1, 2, 3, 2. Right, this one actually repeats. Okay, so I'm just gonna make a few observations here. Suppose we're playing a game where every position allows moves to at most k other positions. And I call that set WX. When I take the position X, if there's a most k other positions we can get to, there's a most k numbers in that set of Grundy numbers for the things that I can get to, right? There's a most k in this set. Well, if there's a most k in that set, I can't have used the integer 0 and the integer 1 and the integer 2 and the integer 3 all the way up to and the integer k. There's k plus 1 integers there. I can't have used them all. So one of those has to be available to be the max. And my Grundy number then has to be most k. So anytime I have most k positions that I can get to from X, the Grundy number of X has to be most k. That's just a kind of a trivial thing, right? And that's for any game. That's not just for these subtraction games. That's for any game at all. Oh no, mathematics is showing up. Yeah. Let's go back and think that we're playing this one heap subtraction game, a little bit more general than the 1, 3, 4 game. Let's say I can take M1 or M2 or M3 up to MK, but I'm just doing one heap, right? I can take any one of those numbers and I might as well just put them in order so that I can say the largest one is R. And I'm going to look at what happens for Grundy number 0, Grundy number 1, Grundy number 2, and so forth, right? It's a sequence of numbers. And when I want to calculate the Grundy number for n, I'm taking away either I'm looking at n minus m1, n minus m2, up to n minus mk. I'm never looking further back than n minus r. So the values of the Grundy number n minus r plus 1, up to n minus 1, those are the only things which contribute to the Grundy number for n. Nothing before that really contributes to it. Okay, there are only k possibilities for each one of these guys. And there's only r of them, so there's only k to the r possibilities for that subsequence. All right, so there are infinitely many concurrent sequences, subsequences of like r in here, but there's only finitely many choices for the values of such a sequence. There's only k to the r of those. Something must repeat. And once something repeats, the next one repeats, and the next one repeats, and the next one repeats. And so what happens is, for any one heap subtraction games, the Grundy numbers must eventually become periodic. They're not always periodic right from zero, but eventually they have to be periodic. And I don't bring any examples with me to show someplace where they're not, but I've seen examples of subtraction games where the period starts at 60 something, all right? And I'm sure you can make it start as far down as you like, but I'm not going to write a theorem on that either. So they're eventually periodic. And anyway, so let me go back. This two heap game. So in fact, now I'm giving you a more general game. All right. So on the first heap, I can take 1 or 3 or 4. And on the second heap, I can take 1 or 5 or 6. And now I don't expect you to know what the Grundy numbers are in these cases, but if you wanted to work them out, it doesn't take you very long. Okay, we know the ones for 1, 3, 4, they went 0, 1, 0, 1, 2, 3, 2, right? And the ones for 1, 5, 6, I don't know, probably mod 7 or mod 11, I don't know, okay? Anyway, you calculate the Grundy numbers for heap A, and you calculate the Grundy number for heap B. If the two Grundy numbers are the same, you're in a losing position. You make some small move again and hope your opponent doesn't know how to play. If the two Grundy numbers are not the same, obviously one's larger than the other. For that larger one, let's say that heap A has a larger Grundy number than heap B. Remember, in game A, I'm playing this 1, 3, 4 game. In game B, I'm playing this 1, 5, 6 game. But let's say the Grundy number here is bigger for a second. What you do is you say, well, find a new heap that you get from A by taking away the allowed amount of checkers that you can take, so that the Grundy number for that new heap is the same as the Grundy number for B, right? Remember, because the Grundy number A here, is bigger than B, well, from the Grundy number A, I can get from A to games with Grundy number for A minus a 1, the Grundy number for A minus a 2, the Grundy number for A minus a 3, all the way down to the Grundy number being 0. Right? So I can definitely get to the Grundy number for B, whatever that is. And that's the move I'm going to make. Now I can always win the two heap game. I've got some work to do. If I want to do it, I have to write down the Grundy numbers for here. I have to write down the Grundy numbers for here. But once I've got those written down and I sort of learn what those are, then I can play that game over and over and over again. And I'll always beat people if we start with a random position and it's a possibility to win, then I can always win. If it's a position where the other person can win, I can hope they don't know how to play, they'll make some errors somewhere along the way, and then I'm all right. Okay? So that's with two heaps. I bet the next one is, what do we do with three heaps? Okay, that's what it is. What do you know? So if you're playing with multiple of these heaps, multiple games, and it doesn't have to be this subtraction game, it can be other games, all right? So later on, I'll talk about the caterpillar game if I have time. We got the subtraction game. I could be playing, subtraction game with one set of numbers, subtraction game with another set of numbers. I could be playing a caterpillar game. There's other games I could be playing that, as long as they have this Grundy type structure to them, I just work out the Grundy numbers for the positions. And what I'm going to be doing is I'm going to reduce to a different game. I'm going to reduce to this game called NIM. All right. Now, the game of NIM, for all intents and purposes, is the start of combinatorial game theory. All right. before 1902, I don't think anybody had completely solved any particular combinatorial game. So this is kind of the first one. Fellow named Bhutan, not the one who works here, because if he was, he would have done this 121 years ago. He doesn't look that old. Okay. Also spells his name differently. So the game of NIM, I'm going to tell you what that is. But this is a really simple game. But I like games with simple rules. All right. Rules have to be kind of simple. My subtraction games, you're taking either 1 or 3 or 4, or maybe in this file, you're taking 1 or 5 or 6. These are really simple rules. You can play with a 5-year-old. Hope you can beat the 5-year-old now, but you can play with a 5-year-old. Okay. So in NIM, what you have is you have a collection of heaps. Now the rules are going to be that what you're doing in your turn is you're going to choose one of the heaps. Okay. And what you're going to do is you're going to remove some checkers from that heap. You have to remove at least one, otherwise the game didn't change, right? But you can take 1 or 2 or 3 or 4 or 5, all the way down to, I can take the whole heap. Okay? That's a pretty simple rule. So we've got here,
Need more, hold on again.
you've got,
Trying to match your things. 3.
I don't care, you've got 3 piles here, and you can take some number from one pile, and then I'll take some number from another pile. And you take some number from one pile, I'll take some number from another pile, and so on. Okay? So that's how we would play this game. Let's do it up here, because give me 3 numbers that aren't too big.
3, 5, and 6.
Just for that, I'm gonna let you go first.
I would like to generously let the speaker go first.
Okay, I don't know if you know how to play, so I'm going to make a move and see what happens.
Okay, let's see. Wait, so I will remove 2 from 5.
You're gonna remove 2 from 5. I'm gonna take this whole pile.
Yeah, I will take.
Reduced it to 2 piles. Which means I'm gonna play a mirror.
Yeah. Yeah, lost. Yeah, so take all 3, then I lose. Yeah. So yeah.
So you actually put me first in a losing position.
I forgot how to play them.
3, 5, 6 is a losing
Yeah,
position, it
yeah.
turns out, okay?
Mhm.
So I made a move, which gives you a chance to win the game. But you have to know
Yeah.
which move you now need to make. And you didn't make a move that I recognize as winning move. So I saw, oh, I can jump on this and I can put myself into this winning position. Mirror position is really, really easy. Okay. So 3, 5, and 6 is kind of a trick question because that's actually bad.
Mhm.
How do we decide what's a good position and what's not a good position? And here's what this fellow Bhutan said. He said, suppose I had that position 3, 5, 6. Well, I'm going to write down 3 in base 2. And I'll occasionally write it correctly. All right. So I'm going to write down 3 in base 2. I'm going to write 5 in base 2. And I'm going to write 6 in base 2. Okay? So that part's easy. You're just going to write things in base 2. Okay? If you want to teach this to a young kid, they have to be able to understand base 2 to some extent. Okay? Not much, but a little bit. What I'm going to do is I'm going to treat these as if they're in columns. And I'm going to add them. So 1 plus 1 is 0, plus 0 is 0. Okay. Do some very standard addition. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. So far, you're with me. 1 plus 1 is 0. That's the only difference, okay? 1 plus 1 is 0 today, okay? So maybe if I put a little star around this to sort of remind you that there's something strange going on with my additions, okay? So 1 plus 1 is 0, and add another 0, I get 0. 1 plus 0 is 1, add another 1, I get 0. And 0 plus 1 is 1, plus 1 more is a 0. And what I have, this thing that I tend to call a checksum, is equal to 0, right? It's all zeros across the board. That's the position you don't want to be in. You don't want to have that checksum being 0. Put this up on the screen for a second. I want to take those, add those things as if I'm adding in base 2, but nobody likes carries anyway, so I'm not going to do any carries at all. I'm just adding them in the column. Nothing gets carried. I take that 0, 1, 1 plus 1, 0, 1 plus 1, 1, 0. I get 0, 0, 0. Okay. So what happens here is if I have k heaps of sizes h1, h2 up to hk, and you get a checksum which is all zeros, you're in a bad position. That's a P position. Right? You don't like being there. Any move that you make leaves a checksum which isn't 0. You make a move and you do something to one of these here, it affects this checksum, and the checksum's no longer all zeros. So if you're at a place where the checksum is 0, any move you make takes you off of 0. A little bit harder to see is that if the checksum is some number m that's not equal to 0, is actually a move which is good for us. Okay, I'm not going to go through the theory of that. It's not that hard, but I'm not going to go through it. But here's what you do. You calculate h1 plus m in this funny addition we're doing, adding them as if they're in base 2 with no carries. Okay. Calculate h1 plus m, h2 plus m up to hk plus m. For one of these at least, some hj plus m will be less than hj, and that gives us the winning move. Well, it's like a winning move. We reduce heap j from hj checkers to hj plus m checkers. Okay. There actually will always be one that works. There'll actually always be an odd number of winning moves. Okay. It actually corresponds to the column that where the checksum is first non-zero, basically. That column will control, has an odd number of entries, and so I get an odd number of winning moves. Okay. So now you know how to play that. Of course, it means you got to keep stuff in your head. Right? So if I have let's just do this with small numbers because otherwise it takes me a long time. But if I have something like a pile of height 1, a pile of height 3, a pile of height 5, and a pile of height 7, what's the checksum? Okay, 3 plus 5 is 6, 6 plus 7 is 1, and plus another 1 is 0. Actually, the checksum is 0 here. That's a bad position to be in. Okay, how do you actually add these things fairly quickly, right? Because you don't really want to spend time writing down 3 is this, and 5 is this, and 1 is 0, 0, 1, and 7 is 1, 1, 1, and then doing the addition. You can do that if you want, but you can do things a lot quicker if you're willing to play up to a certain size and you're willing to use a few memory cells. So you can write down an addition table for this type of sum, and you can say, what is 7 plus 6? Well, I go across the line for 6. I go to 7. 7 plus 1. 7 plus 6 is 1. And if I want to do 3 plus 5, here's 3. Here's 5. It's in this column. So 3 plus 5 is 6. Notice 3 plus 6 is 5. And 5 plus 6, where's 6? Up top here. 5 plus 6 is 3. This is a funny addition, isn't it, right? 3 plus 5 is 6. 5 plus 6 is 3. And 3 plus 6 is 5. So actually, I really just have to remember that triple, 3, 5, and 6. That if I'm in that triple, addition of 2 of them gives me the other one. Now, we actually call this Nimber addition because it's for the game NIM. All right. It's not a type. There were lots of typos in the slides. I got most of them out. There's still at least one because when we were reading it over last night, I said, well, that's incorrect grammar. And my wife said, leave it in because people don't talk like they have correct grammar. So there's one that we left in because otherwise people say that's weird. Okay. I think Conway had it memorized out at least to 15 plus 15, right? So the table is 4 times as big as this because there's twice as many rows, twice as many columns. And so if you're playing a game with only up to 15 at the most in each pile, he could play this very, very quickly. All right. This addition has some neat properties. I'm not going to go and prove these either, but you have the commutative property A plus B is B plus A. You have the associative property A plus B plus C is A plus B plus C. And you also have additive inverses. A plus A is 0. Maybe not, may not be the inverses you like, but negative A is actually A, right? Distributive property also holds, things like that hold, all right? Okay, I'm going to talk about some other versions of this game. So 1930s, chess champion Emanuel Lasker, world champion, right? And he introduced a variant of NIM. Did it in an obscure place. It took me forever to find an actual reference for it for one of my papers. So in his game of NIM, you could do the regular NIM moves, or you could pick one of the heaps and split it in 2. Yep, by splitting into, you have to split it into 2 non-empty heaps. Can't say I'm going to take a heap size 7 and split it into 7 and 0. No, you can take 7 and split it into 3 and 4, or 2 and 5, or 6 and 1. Right? Okay. So how do you play this version of NIM? Well, for each pile, for each heap, you work out what the Grundy numbers are. The Grundy number of 0 is 0, 1 is 1, 2 is 2. Nothing tricky up to here. Absolutely nothing tricky up to here. When you get to 3, you have a move that I can take it to a pile of height 0, which is Grundy number 0. I can take it to pile of height 1, which is Grundy number 1. I can take it to pile of height 2, which is Grundy number 2. Or I can take it to one pile of 1 and one pile of 2 by splitting it, and that's 1 plus 2, and that's 3. Even in the Nimmer edition, that's 3. Okay, so I can get 0, 1, 2, 3. The first one I can't get is 4. And then for 4, actually, I can't get 3. So Grundy number for 4 turns out to be 3. And they follow this type of pattern that 5 will be 5, 6 will be 6, 7 will be 8, 8 will be 7. So the multiples of 4, except for this one, okay, the multiples of 4, it drops by 1, and the multiples of 4 plus 3, it goes up by 1. So you can learn what the Grundy numbers are for that. And then you play Grundy numbers on, you play NIM on the Grundy numbers of the heaps. I'm not going to do that here, but it's another example of a completely analyzed game. Okay. I'm not going to show you much more than that. I'm just going to go through some variants of these things. Actually, I showed this Lasker's NIM to a recreational math class. It was for students in the MST program, I think mainly. And a student in that class asked, what happens if instead of having the move where you're allowed to split a heap, what if you have a move where you're allowed to take 2 heaps and put them together? Now we're in strange territory. Even in the case where there's only 3 heaps, I can only tell you the winning strategies up to, one of the heaps having up to 11 checkers in it. And 11 checkers, there's a, what I call the sporadic piece before you get to the eventually periodic piece. The periodic piece, when you get to it, has length 960. So you're not going to keep this in your head. All right. I'm not going to keep it in my head. So it's kind of strange. When I first saw it, I thought, well, this won't be too hard. But here you go. This is an unsolved problem. As far as I know, it's completely unsolved, except for the stuff that I've done before. Okay? It's fun. You can write a paper that shows, I don't know how to solve this. That's basically what that paper is. Here's an interesting game. I don't know how to solve it. Maybe somebody else can figure it out. Okay. Here's another one. This was for a mathematical problem solving class, which is the MAT 4937 for those of you here. I wanted to give them a project which would take 2 or 3 weeks. And as I was walking to class, I do things at the last minute, right? I'm walking to class, I'm saying, what project shall I give? And I thought, well, I can give them last year's NIM, but the web's here. If I had done this 30 years back, they wouldn't be able to look on the web and find out how to do it, right? Now they just look on the web and boom, they got the answers. It's no fun. So I said, let's change it. So instead of doing last year's move of splitting a heap, I'm going to say what you can do is you can pick one of the heaps, you can add 2 checkers to that heap, and then you can split it into 2 pieces which are smaller than that original heap was. So if I have a heap of size 7, I add 2 to it, I get 9. I can split it as 6 and 3, because 6 is less than 7, or I can split it as 5 and 4. Okay? So I can split it up a couple of ways. So I gave that problem to them. I think I gave them 3 weeks to play with it. And about a week later, Krista, just in class, you give students instructions, right? I actually told them, you can work with anybody else in the class. Okay? You can work together, not a problem. If you turn in a joint thing, of course, you got to put both names on it or all 3 names on it or whatever. But they weren't supposed to talk to anybody else. You don't know how well that worked with students. Okay. So I didn't have a solution to this when I gave it to them because I thought it up on the way to class. About a week later, I came in and said, well, here's how I think the Grundy numbers behave. And I'm not telling you how the Grundy numbers behave, but it's actually something quite simple, okay? But it means looking at the bit pattern and deciding something based upon what the bits look like. The base 2 representation, okay, for those of you who have never done computer science. So I gave them a conjecture, and when they turned in their projects, not one of them wrote down what that conjecture was, that I'd written on the board and said, it behaves like this. Not one of them wrote that down in what they turned in. One of the students put the problem on Stack Exchange. So now the whole world knows the problem. And one of them went to a graduate student in the MLC. If you're not here, that's the Math Learning Center. The graduate student that they went to came over to see me and said, some student told me about this problem you gave in class. I know he's breaking the rules by coming to the Math Learning Center, but I like the problem. Okay. So he and I got together. We modified the problem because this would be a boring problem to write a paper on by itself. We said, let's do it where we pick a number Q, fixed integer Q, and you add Q checkers to the heap, and you can split the heap into 2 heaps smaller than the original. Okay. And I don't care if Q is negative or positive. If you add -5 checkers to a heap, you're taking 5 checkers off the heap. And now when you split it, you get 2 smaller things. It doesn't really bother me. Okay. So the cases are Q is odd or negative. Don't care what the other person does. You just play regular NIM. Okay. Q equals 0, that's last year's NIM. Q equals 2, that's a problem I gave to the class. And we completely solved it, of course. And Q even and greater than 2 is a different case, and it's a bit more complicated than the other cases. But if you want to see the proof of that, I brought the proof of that one with me because it's the nicest paper I have in game theory. So I have a copy of that one. Okay. We wrote it up. I sent it into the journal, Discrete Mathematics, and I told my graduate student, Discrete Mathematics takes about 3 years to publish anything. And they published it 6 months after we sent it in. And I said, that's probably never going to happen again. I think he thinks I lied to him now. Okay. Here's another version. Again, I don't know how to play this. All right. So in the game, you're allowed to have a pass. Just one in the whole game. You're playing regular NIM, except now there's a pass. All right. So I kind of think of that as you have a heap with 1 differently colored checker. So all your checkers are red, let's say, and you've got 1 green checker. All right. That's in a pile by itself. And anytime during the game, when it's your turn, you can take the green checker, except you can't take it when all the other piles are gone. I slipped into saying piles instead of heaps. Game theorists don't like it when I say piles instead of heaps. Okay, so I had piles all through this and I went through and changed it, all right? So guess what? We don't know how to play this. Simple modification. You can take a pass at any time except for the very last move. And the rest of the time, it's just like it looks like regular NIM, but it doesn't behave the same. So we can actually answer it if you have a bunch of piles. That's a mathematical term, bunch. Yeah, you have some number of piles, but none of the piles have more than 4 checkers. Okay, now we know how to win. And we had some ideas of how to do it with 5 piles, but that's not that exciting, right? But we wrote it up and a journal took it, so what can you do? Here's a game called Bulgarian Solitaire. Some of you may have seen this. Nobody's Bulgarian here, right? Because I think they chose Bulgarian Solitaire. I don't know why. I don't think it's in honor of any Bulgarians. So you have several heaps of checkers on the table, and a move consists of taking 1 checker from each heap and making a new heap with those checkers. Some of our professors, when they're teaching the mathematical computation course at the 2000 level course, they like to give this as a programming assignment, just to run this and to see what happens, basically. And what happens is eventually it cycles. So let's say I have heaps of size 5, 4, 5, 2, 8. Well, if I take 1 from the 5, I get 4, 1 from the 4, I get 3, 1 from the 5, I get 4, 1 from the 2, I get 1, 1 from the 8, I get 7. And the new heap has 5 in it because I took 1, 2, 3, 4, 5 away. All right. Only 1 player is needed, and that player doesn't have any choices. So it's really a 0-player game. I would have thought 0-player games would be nice. That's what Conway would have called the game. You've all heard of Conway, right, from the Game of Life, which is a very famous 0-player game. It's basically a computer in disguise. Right? It's got very simple rules, but it acts like any other computer in the world. Right? That's strange. So if you keep making moves in this game, what happens? Well, there's only a finite number of ways you can put together the heaps. There's only a certain number of partitions of the number n. And so what happens is you have to come back to the same position over and over and over again. What's maybe surprising is that position, if I start with n checkers in my heap, and n checkers in my collection of heaps, total of n, basically come down to 1 pattern with a small variation. You basically come down to a triangular shape with maybe 1 extra on some of the heaps. But here's playing a game starting with 5, 4, 5, 2, 8. I just started running it out until I saw there was a repeat. And then I looked backwards and, oh, it repeated here. Oh, it repeated there. Oh, it actually repeated here because 1, 3, 4, 4, 5, 7 is really the same as 1, 3, 4, 4, 5, 7. Right? The order doesn't matter to me. But something kind of nice happens as you're doing this. I keep adding the newest one on the end. And eventually they all come out, they get in order and they stay in order, right? Kind of nice that happens. If you want to see why that happens, I have that written up on the web. You can look at red, green, Bulgarian Solitaire. You'll see a fairly easy proof as to why it comes down to that type of triangle. As I say, this looks like the triangle 1, 2, 3, 4, 5, 6, all right? With an extra 1 on the heap of size 0, and an extra 1 on the heap of size 3, and an extra 1 on the heap of size 6. So this looks like 0, 1, 2, 3, 4, 5, 6, with 1, 2, 3 extra checkers in a certain place. And if you look at the previous one, it also looks like 0, 1, 2, 3, 4, 5, 6, with an extra 1 here, and an extra 1 here, and an extra 1 there. Right? So that extra ones actually cycle around in a nice pattern. It's a silly game, but I put it in there because later on I will mention, in fact, this next one, I will mention that. So for some reason, I like dreaming of games, and I send them to my co-authors and they say, oh, I like that one. And then we start working on it. So this is a game, I have 2 players, I call them Alpha and Omega. And I wanted to use terms which I don't say he and she, but I said it's, right? They're not necessarily humans, all right? Two players, and alpha has lots and lots of moves, and omega has only a few moves, okay? So alpha, when it's its turn, can take some collection of the heaps and take one checker from each of these selected heaps to make a new heap. I just don't let it take, if there's one pile, if there's a pile of height 1, I don't let it take the pile of height 1. Okay. Player omega just gets to do Bulgarian solitaire. But now I've set the rules up so that if after you make the first move, if there's any two heaps whose size differs by 1, then omega wins. So omega has almost no moves. Omega plays like an idiot. But the odds seem to favor omega a fair bit here, right? If it comes out that any two heaps, is a heap of size 6 and a heap of size 7, omega wins. So alpha only wins if alpha can keep playing forever. So are there positions where alpha can win? Well, here's one. Right? If I have heaps of size 1, 1, 3, 3, 5, 5, 7, 7, I take 1 away from each one of these in omega's move, let's say, I get 0, 0, 2, 2, 4, 4, 6, 6. And I've taken 8, so I get an 8. So I get to 2, 2, 4, 4, 6, 6, 8. If I take another omega move, I get back to 1, 1, 3, 3, 5, 5, 7, 7. So if I'm in this position, alpha can win by just playing omega's move, all right? So alpha stays alive. And you can do this if you have 2m squared, right? There's 18 here, right? I think, no, maybe not 18. Let's see. 7 plus 7 is 14, 24, 30, 32. Okay, so there's 2 times 16 there, right? 2 times the square, okay? Anytime it's 2 times the square, I can write that type of pattern. Alpha can win if he's in that pattern. So there are an infinite number of places where alpha can win. Are you trying to tell me time's up or you just want to? I'll keep talking forever, but this game, when I saw this game, this is a caterpillar. So this is what I would call the spine, and these are legs. Okay, and what you do in your turn is you pick a path. So you might pick this path. Right? You pick a path, and then those edges go away. And the next person picks a path, can't use any of the edges you've taken away. Next person picks a path, and they take away those edges. And you keep doing that. There's only a finite number of edges. Eventually, the game stops. The one who takes the last edge wins. Okay? When I first saw this game, I wasn't super excited with it. It was Frank Harari that specified the game, but I did write down some things about how to win it. And eventually, some friends of mine wanted a paper to write. And I said, well, how about this? We can actually win in 95% of the starting positions. That's not too bad. And the way to win is basically to take all of the spine and at the left end, either 0 or 1 edges, and at the right end, either 0 or 1 edges. That's the basic strategy. There's another strategy that goes in there. Anyway, so that one showed up. Here's one where you have some checkers on a checkerboard. You can take a whole row of checkers from the board, and they're not necessarily, they're spaced randomly. They're not necessarily all the checkers in one row. You know, every row is not full. Some rows may be, but some rows may just have 1 or 2 checkers in them. You can take everything in one row or one column, and the one who takes the last checker wins. Don't know how to win that one either. Game of Divisors is an old game. Came out in 1958, and then nothing happened till like 1975 when Martin Gardner put it in mathematical games, and then people got interested in it. But it was a smaller version of it. You pick an integer and you you list all of its divisors, and then at any turn, you take any number that's still on the list, you cross it out and all of its multiples. And if you take the number 1, you lose. So you're taking numbers on the list, till the list gets down to just the number one, and now you lose. So who wins? Actually, the first person can always win. I have no idea how. I can prove the first person always wins. I don't know what to play to win. Isn't that strange? Okay, this may be the first time you've seen something like that. First player can always force a win, nobody knows how. And the way you do this is you say, suppose I took that number n, the biggest number, that might be a winning move. Okay, I'm done. If it's not a winning move, the other person takes some number k. In taking k, they take everything that k divides into, and they take the number n as well. So why didn't I just take k to first move and then I would have won? So it's called strategy stealing. If they have a way to win, if I take the number n, then I just play the way they would have played, all right? Whereas maybe if I just take n, that's a winning move. So there's always a winning move for the first player, as long as n's bigger than one. Nobody knows what the strategy is. I can tell you in one specific case, but that's not that exciting. There are a couple of cases I can tell you. If n is p to the k, q to the k for primes p and q, yeah, it's easy to win. Okay, you take the entry PQ and that really reduces it down. And if n is of the form p times q to the k, you can see how to win. And there are a couple of cases where you can see how to win, but it's not that easy in general. Okay, so another version is what happens if you try to say the person who takes the last one loses, which is what happens in the game of divisors. That's called a misère game. If the strategy is the same, more or less, as it was in the regular game, the game is called tame. So misère nim, you play just like you play nim until you get right near the end. Nim is called a tame game. And I will stop there because they're looking at me saying, you're a pork stew. No. Okay. Anybody learn anything? Anybody want to work on game theory? Got lots of games I don't know how to solve.
So I have a question. Have people studied the computational complexity of these kinds of games?
So you mean if I give you a position, how long it takes me to try to figure out what a winning move would be?
Well, maybe not you, but like how you could program a computer to do it.
Well, see, I almost always take the game and write a computer program. And usually you kind of do this inductively, right? You'll figure out how to win for, a pile of 0, then 1, then 2, then 3, then 4. So that when you come back and look at something, you're just looking at the previous ones. So there is kind of whatever the depth is times the length of the list. Now, if you're trying to do this out to 200 million, you need a lot of storage to do that way. But as I said, you really only need to look at the last few. So I can just store, if it goes back R positions, I can just store the last R and I can cycle it around that way. So I can, in some of these games, do it in n times the depth I have to do R. In this one, this is messy. So many different configurations show up here that we weren't calculating Grundy numbers for the whole thing. Once I take things away, I have smaller pieces and I can calculate the Grundy number for this and the Grundy number for this and the Grundy number for this and the Grundy number for this. So I can do the Grundy number for small pieces. And I can either leave two, one type like this on the end and one type like that on this end. Because if I just do this, the Grundy number for this will probably not match what I get over here, which is, this is Grundy number 2 total. This is something else. I doubt it's a 2. I don't memorize how to solve it once I've written down the cases. So on that one, because it's messy, it's like, if we use this strategy, which quickly separates it in a bunch of pieces, I can solve the bunch of pieces and then we're okay. And that works 95% of the time. So I don't try to solve it for all the other cases.
Probably was a big proponent of playing games, right?
Yes, and if you want an interesting book to read, you can read his book on numbers and games. It defines A game, as I said, it's an ordered pair, right? The left element of the ordered pair is a set of games, and the right element is a set of games. So it's defined inductively. Doesn't tell you the basis, so the basis is, well, I can have the empty set of games for both the right and the left argument, and that's a game. So that game, which has no moves, that's a game, right? So once you got one, then you can use that game as, the set containing that as the left or as the right or as both, and see what you get and so on, right? So that's how he defines games. He defines numbers very, very similarly, but you have to have a relation less than, which is defined at the same time you're defining numbers as two definitions that are linked together. One of the interesting things about the way he defines numbers is if you ever did Dirichlet cuts, the multiplication is ugly. Conway's notation, the multiplication is not so ugly. It's uniform for whether the numbers are positive or negative, or infinitesimals, or ordinals, or his type of ordinals, and so forth. If anybody would like to look at more detail, I do have some papers up here I can pass out to you. Okay.
Great, thank you very much, Dr. Locke. That was a wonderful presentation. So from AWM, we have a token of appreciation for Dr. Sander and Dr. Locke for giving wonderful presentations here today. So if Dr. Sander, you can come up here.
Data cuts, all right. Yeah, data cuts. You don't always get that. Thank you very much.
Great. So thank you guys very much for such wonderful talks and for attending our event today. Thank you.
Yeah.
I love the fact that there's a blue nim across your forehead. There's a blue
Oh, yes.
nim across your forehead from the projector.
I can see it in my eyes, so it's even better. I'll just come over here.
Yes.
Okay.
Thank you again. Thank you very much. Yeah. So the next session will be the career panel discussion. So we're gonna start in 5 minutes. So we would like to have the table for career panel. So thank you.
A question on my final for game theory, when Dr. Walorski taught it, was a staircase nim. That was a version I played. It was I think the moves were you could take a heap on a stair and move it up, or you can move it, I think you moved it down. And I think,
There's a game called Silver Dollar Nim.
yeah,
And you have some silver dollars on a one-line checkerboard, and you can only move them to the left.
I think it was very similar to that.
And you actually kind of play them on this basis. Yeah, any of them that you want, you are welcome to take. Provided lots of copies. This one is the best one. It's got the most mathematics in it.
We're serious. I can see that. Sorry. I failed the intelligence test here. How could it work?
Oh, and then let's
I'm sure it's fine. This will be helpful. Yeah, yeah.
It was